Let's begin with the details of our today's lecture, that is belonging to the pre-formulation. So very good morning to all my dear students. Let's go through the industrial pharmacy first. So we are studying the pre-formulation, and these are the contents that are related with our this particular lecture. In our previous lectures, we had already studied the definition of the pre-formulation, the crystal structure, the amorphous form. Then we have studied the polymorphism, the solvates, hydrates, the classification for the polymorphism, that is the enantiotrop, monotropes. Then we had gone through the solvates, hydrates, the different classes of the solvates, that is the class 1, class 2, class 3, the different examples of the hydrates, and the details associated with the polymorphism. We are on to the next property, which is said to be the solubility. And in that also, we had covered the details associated with the need of solubility, then the significance of solubility during the process of pre-formulation, what is the minimum expected solubility, and how to determine the nature of a drug and the need of a salt formation. So if you see that if the drug that will be having its solubility in case of acid, we can think that the nature of the drug, that is the weakly acidic. If the drug that is having its solubility in case of the bases compared to that of the FPS, we can say that the nature of the drug is the weakly acidic, and these drugs, they will require the salt formation, right? So now today what we will see, we will go through the salt formation and the other details. So let's come to the salt formation. For which particular type of drugs the salt formation is advisable? From the last lecture, the last topic, that is the tabular distribution, in that we saw that the weakly acidic and weakly basic drugs, these are the targeted drugs which will require the commonly using the formation of the salt. But that is not the case associated with the strong acids and the strong bases, because the strong acids and strong bases, these are soluble, so there is no need to go for the process of improving the salt formation and the solubility. These are also hygroscopic one, but that is not the case associated with the weakly acidic and the weakly basic drugs. So these drugs, they need to be the salt formation. The less soluble salts are intentionally used, right? Every time we need not to go for the salt formation and to increase and to improve the solubility. Sometimes intentionally we are going for using the less salt formation or the less solubility. That is for some specific purposes, used for specific reasons. Now what are these reasons? The first one is the masking the test. Like say the example of the chloramphenicol palmitate, protecting the parent drug from excessive degradation in the gut. This is the second reason. And the third reason is that the sustained release form of most of the drugs. So these are the three reasons for which it is not advised to go for the salt formation or the low solubility that is advisable. That is to mask the test in case of the chloramphenicol palmitate, to protect the parent drug from the excessive degradation in the gut by the gut enzymes like say the erythromycin propionate. And if you want to sustain, if you want to maintain the release of a drug for a longer period of time in a predetermined fashion, then in that case it is advisable not to go for the salt formation and to have the low solubility. So that is a classical example of the propranolol laurate. So in case of propranolol, a drug subject to first pass metabolism, the hydrophobic laurate counterion was selected in order to reduce the aqueous solubility and dissolution rate, thereby sustaining its release. The drug that will get degraded by the first pass metabolism, right? So because of that, the concentration of drug that will goes down. If we are not allowing the drug to get into solubilize quickly and to absorb at a faster rate, then definitely this process of first pass metabolism that can be inhibited, and thereby we can go for the sustaining its release, we can go for maintenance of its release. When tested in dog, the propranolol was tested in the dogs. The laurate salt resulted in improved bioavailability compared to the hydrochloride salt in immediate and the sustained release formulation. So the propranolol, it will be having its salt form like say the propranolol laureate, propranolol hydrochloride. So the propranolol laureate, it is the particular kind of the salt which will be having sustained effect, which will be having the low release profile. Now again recall the things associated with the pre-formulation. What we want is we want the stable, we want the effective, and we want the safe kind of formulation. So that's why it is very necessary to study the solubility in terms of all these are concerned. But in addition to all these, we require the efficacy also. Efficacy, that is in vivo effectiveness. Effectiveness, that is the in vitro safety profile. So these are the selection criteria of suitable salt. But using the salt form, the efficacy doesn't vary salt to salt of a parent drug until the dosage is increased very highly. So the efficacy that will depend on to the dosages of the drug. Biopharmaceutical properties like dissolution rate, onset of action, duration of action, concentration at a particular site, Cmax, that is the maximum plasma concentration, Tmax, that is the maximum time necessary to achieve the plasma concentration, and stability, that will vary with the salt selection, right? So again, as we had discussed just now, the propranolol laureate and the propranolol hydrochloride. So propranolol laureate, that is differing in terms of all these are concerned. So the percentage use of salts in pharma industry, if we want to see, we can just have a look onto these different types of the salts. These are very commonly used in case of the industry. The drug that is available in hydrochloride form, sulfate form, maleate form, potassium form, sodium form, and the calcium salt form. Now, if we have a look over onto all these, it is a particular maleate form which is least used in case of pharma industry, and it is the sodium salt which is highly preferred one, almost up to 62%, followed by hydrochloride salt 43%, followed by calcium salt 12.9%, followed by potassium salt 10.8%, followed by sulfate salt 7.5%, and the least percentage of use in pharma industry that is associated with the maleate salt. So we need to improve, we need to modulate the solubility of a drug, and there are these number of methods which are very quietly used in case of pharma industry. That is the use of co-solvent, hydrotrophy method by addition of polar groups, use of solid solution, solid dispersion, eutectic mixture, micronization, use of surfactants, alteration of pH of solvent, use of suitable crystal form or metastable polymorphs, solvate formation, selective absorption on insoluble carrier, cyclodextrin complexation, and last but not the least, it is the phospholipid complexation, right? So these are the methods which are used somehow or rather based on their effectiveness, based on their usage, based on their compatibility, based on their uh, easy steps that are involved into that one. As far as our study point is concerned, we need not to go into all the details, but if you want to go through, you can just type the method into the Google and you will going to find the details associated with that. Almost if we go on describing a single method, it may take at least 10 to 15 minutes to describe it, right? And as far as our scope is concerned, we are more concentrated from curriculum point of view onto the solved form, right? But you should know that what are the other methods. So here is the list of the same. If you want, you can go through the details of the same. So what we saw up till now in this particular lecture, we saw the how the salts that is going to be formed, what is the need and to which the salt formation that is applicable. It is applicable to the weakly basic and weakly acidic drugs. There are specific reasons that why we want to reduce the solubility, like say in order to mask the test, in order to improve the release pattern. Then we saw the salt formation. Then we had gone through the number of methods that are used in order to improve, in order to modulate the solubility. Now we will see that what is the intrinsic solubility, what is the calculating intrinsic solubility, how to calculate it, its definition, classification, and how to measure the solubility. So this will be the focus of our discussion here onward for few minutes. So what is the intrinsic solubility? It will be represented as capital SO, that is sub O or the subscript O. So solubility of a pure weak acid in acid and pure weak basic in alkali is called the intrinsic solubility. So what is intrinsic solubility? Just to remember, same. And what is the meaning of same? Weakly acidic into the acid, weakly basic into the bases, and their solubility in this condition, that is nothing but the intrinsic solubility. Now it is the fundamental solubility when completely the drug that will remains into the unionized form. Our more concentration, our focus in case of pharmaceuticals, as far as the drug, as far as the APIs are concerned, that is onto the unionized form, because unionized form that is permeable through the biological membrane. The solubility should be measured at two different temperatures. One is at 4 degrees Celsius and the second is at 37 degrees Celsius. It is necessity to measure the intrinsic solubility at 4 degrees Celsius in order to ensure the physical stability and extending the short-term storage and chemical stability. Whereas measuring the intrinsic solubility at 37 degrees Celsius, it is for supporting the biopharmaceutical properties at body temperature, because the body temperature that is at 37 degrees Celsius, and the drug that will goes inside body and it will shows its effect at this particular temperature. So how to calculate the intrinsic solubility? The solubility of the pure form is determined by the phase solubility diagram, because when we are studying the drug as such, it won't remain into the pure form. It is in association with that of the impurities. So these impurities either may causes increase or decrease into the solubility. So that can be studied by the phase diagram, the amount of drug to the amount of dissolving solvent is varied. So for a particular drug, the solvent which is used in order to dissolve, that will differs, and the solubility that will be noted and recorded. For different solvent, there is a different solubility, and this is to be noted. So this is the particular phase diagram, and particularly for the pure drug, when there is no interaction, there is a constant solubility. Onto the y-axis, you can see the solubility. Now, the presence or absence of these impurities that will either causes increase or decrease into the solubility. So that we can understand through this particular uh, phase diagram, or the solvent phase ratio diagram, or the graph. The solubility of the pure form of API can be determined from the impure form available at the time of pre-formulation stage. Now, we cannot say just by thumb rule that what is the meaning of freely soluble, very soluble, soluble, sparingly soluble, or insoluble. There are specifications. There is a classification which is official into the Indian Pharmacopoeia and the United States of Pharmacopoeia. So based on the parts of solvents that are required in order to dissolve the one part of solute, the different definitions has been given in order to express the solubility for the given compound, drug, or the API. And it is very necessary to remember all these terms and what is their meaning, because most of the time in GPAT examinations, these questions that are very oftenly asked. What is the meaning of freely soluble, or what is the meaning of the very soluble? When we can say that the drug that is very soluble, it means that it requires less than one part of solvent to dissolve one part of solute. Are you getting my point? What I mean to say? There is a one part of solute. Solute is the API. Solute is the drug. There is a one part of solvent. Solvent that is either aqueous or organic solvent, whatever it will be. We do not to bother that what is the nature of the solvent in this case. We just want to clarify our doubt as far as the very soluble and these numbers are concerned. So very soluble means that, let's say for example, if you are taking one part of API, one part of drug, in order to dissolve that one part of drug, how many part of solvents are required? So that number is here, right? So when it is said that it is the very soluble, it means in order to dissolve the one part of solute, we require less than one part of solvent. Is it clear? The same case is applicable to all these. Whenever it is freely soluble, that means in order to dissolve the one part of solute, we require around 1 to 10 part of solvent. When it is said that it is soluble, that means in order to dissolve the one part of solute, we require the 10 to 30 parts of the solvent, right? And likewise, for sparingly soluble, that is for one part of solute, we require 30 to 100 part of solvent. For slightly soluble, in order to dissolve one part of solute, we require 100 to 1000 parts of the solvent. In order to dissolve the very slightly soluble drug, for one part of solute, we require 1000 to 10,000 part of the solvent. And when we require, in order to dissolve one part of solute, more than 10,000 parts of the solvent, in that case, it is said that the drug is insoluble, right? So these are the expressions and these are most important. So how to measure the solubility? In order to measure the solubility, it is very easy. You just add excess amount of solute in a certain amount of solvent at a specific temperature and pH. We need to maintain the temperature and pH constant one. And we have to take the solute, that is the drug or API, and we need to add the solvent into that one. Allow the solution to be agitated or stirred overnight to establish the equilibrium. What is the equilibrium stage? Equilibrium, it is the particular stage that when we are going on adding this solute into the solvent, when it will get dissolved, again, we are going on adding. Now, the stage is there, the point is there when further there is no solubilization of the solute into the solvent. So that particular stage is said to be the equilibrium stage. After the overnight stirring, centrifuge or filter the sample. So after centrifuging and filtering, you need to analyze the sample with the help of analytical techniques like say the spectroscopy or by some other means for knowing the concentration of drug that is solubilized. So these are the steps that are used in order to measure the solubility. So in the last few minutes, what we had studied what is the intrinsic solubility, that is the same phenomena, how to calculate the intrinsic solubility, the definition of the solubility and the classification of solubility. This classification of solubility is based on the number of part of solvent required in order to dissolve the one part of solute, and the process by which we can go for measuring the solubility. Now in coming few minutes we will go through the pH. As far as the pH is concerned, what is the definition of pH? What you know as far as the pH are concerned? The pH, that is nothing but the power of the hydrogen ion. It is alternatively also defined as it is the negative log to the hydrogen ion concentration. And there is a scale which is said to be the pH scale, and the pH scale that will ranges from 0 to that of the 14, and this scale is responsible in order to express the pH of any given liquid or compound or solution. So when the pH that is less than that of the 7, when it is in this range, that is 0 to 7, the particular pH is said to be the acidic. So near to that of the 1, we can say that it is strongly acidic. Contrary, if it is above the 7 to 14, we can say that the nature is basic one, and 14, that is the highly or strongly basic nature. Whereas the 7, that is the particular intermediate stage, which is said to be the neutral one, where there is no any kind of blue or red color formation when we are subjecting it to that of the litmus test. So that is the pH scale. Now, what is the significance of pH in case of pharma, in case of pre-formulation? The significance or the importance is in variety of fashion. When we are going for a particular kind of dosage form, like say injectable types of preparations, there is a strict necessity to maintain the pH. If the pH is not maintained, that may lead to the tissue damage or pain at the site of action or pain at the site of injection. So injections should be in the range of pH that is 3 to 9 to prevent tissue damage and pain at injection site. So the range is between the 3 to 9. So 3, that is acidic, 9, that is alkaline, and in between these there is a 7 which is said to be the neutral one. The oral syrups, they will be having the significance of pH as far as the palatability reasons are concerned. So oral syrups cannot be formulated too acidic for palatability reasons, because that will lead to the irritation of the oral cavity and the gastric mucosa. More alkaline pH, that will affect onto the containers of the formulation, containers of the product. More alkali, that may attack onto the glass container, and that may lead to the leaking of the alkalis from the class. The pH of formulation must not sensitize the site of application. For example, pH for buccal application that should in the range of 6.6 to 6.8. If it is the oral product, if it is the buccal product, it should be in the range of 6.6 to 6.8, because this is most prominent in case of the chewable tablets. There is need to maintain the pH. So what is this pH? This pH is acidic one, as it is less than 7. So for buccal, we require the acidic pH. The GIT that will shows a variety of pH, particularly when we start from the oral cavity, esophagus, stomach, duodenum, to the small intestine, and then to the large intestine. The whole region that is said to be the GIT region, that is the gastrointestinal tract region. And there is a variety of pH as far as the different regions of these GIT tract is concerned. If it is the buccal, as already I told you that it should be 6.6. For stomach, it is 1.2. For duodenum, it is 6.8. For small intestine, it is the 7 to 8. So as far as the intestine is concerned, that is toward the alkaline side. For duodenum, again, it is slightly acidic one or near to that of the neutral one. As far as the buccal is concerned, again, it is slightly acidic one, but as far as the stomach is concerned, because of the release of the hydrochloric acid, it is strongly acidic one, 1.2 pH. So this is as far as the pH is concerned, its significance. Now we need to study the ionization constant. The ionization constant that will be represented or that will be shown as the pKa. So ionization constant, that is the pKa. The strong acids, for example, hydrochloric acid, these are ionized at all pH values, whereas the ionization of weak acid is dependent onto the pH. Right? So this is most important one, the hydrochloric acid that is ionized, or just in order to understand the strong acid, they will ionize at all pH values, whereas the weak acids, their ionization that will dependent onto the surrounding pH, the pH of the gastric region, the pH of the intestinal region. Why this is important? Because our focus that is onto the unionized form of the drug. So the pH of surrounding region, it should be such that it will causes more and more API drug that should remain into the unionized form. So in case of stomach, it is acidic. In case of intestine, it is alkaline one. So if we are going for formulating a particular kind of dosage form, so based on the nature of the API, whether it is weakly acidic or drug, we may go for modifying, we may go for designing, we may go for developing a particular kind of such a dosage form targeting to that of the either stomach or to that of the alkaline region, so that we will obtain more and more unionized form of the drug so that it will get absorbed. The extent of drug ionization at a certain pH, that will depends on solubility, it will depends on stability, it will depends on drug absorption, it will depends on activity, it will depends on pKa. So there is a relationship with all these things, and the ionization that will depend on all these factors, right? And ultimately the absorption of a drug. So what we saw the ionization constant, and there is a relationship between the pH and the pKa. So these are interrelated one will going to affect other, and ultimately the ionized and unionized form of the drug, and at last it will affect the uh, solubility and the absorption of a drug. So because of the time constraint, we cannot continue with the remaining points. So that we will see in the coming lecture. So with this, we will stop at this particular point only. Thank you very much.